So this is the, you hear me? All right. This is the background of this presentation. I was hired at the beginning of the year. I worked there for a few months to bootstrap a new online betting website from scratch, right? And so in online betting, you have, you bet a certain amount of money for a certain ratio. The naming jargon is odds. And if you win the bet, you get the profit, right? So this is the basic operation that you do in that website. And we had a property to guarantee the system. The system had to be a zero-sum system. So in this website, players pay a fee to be able to play, to bet, but what one player wins have to be paid fully up to the last cent from the guy that loses, right? So the system, the company has to put no money into the system. There can't be any creation or deletion of money, you know? It has to be a zero-sum system. And this, the whole feature set of the website posed like very interesting problems. And so I would like to share with you these problems and the way we addressed them. And meanwhile, talk a little bit about number representation in Ruby or in computers. So first thing, when something like this, where there's money related and there are cents and this kind of stuff, first thing, no way we are going to work with floats. Mostly of you already know that floats have issues, right? So the forbidden float is the correct name for this title. You know these kind of things happen. You know that you are subtracting something that gives a result that is not the result that Ruby gives you back. So you all know this, but just to give context to the presentation, remember the positional system. So we have this number here in base 10, and this means, this notation for, so this is the digits, and these are the exponents of the base, or radix, right? And for the fractional part, you go with negative exponents, you know? All right. So you probably know this is the internal representation of doubles, you know, in the computer. And in Ruby, you can assume that you are, maybe in some esoteric platforms, it could be that Ruby MRI compiles where this is not, you know, the internal representation, but in general, you can assume you are working with doubles like this, you know? There's a sign bit, there's an exponent, and then there's a mantissa. This is the underlying double thing that is wrapped in air float, and in recent versions of Ruby, there's an optimization where, well, this is tagged in a pointer, but anyway, it doesn't matter. Let's focus on the standard representation of doubles. This is the way you interpret that as a number. This is the sign. There's an implicit one. Well, there are some edge cases and different cases because that standard, it's like, you could give an entire talk about that standard, but let's talk about, you know, the majority of numbers are represented like this. So this is the fractional part. There's an implicit one that is not in, you know, stored. It's implicit, and then you do some operation with the exponent. Doesn't matter. So why is this false? So the thing is that this is the internal representation of those numbers. So in this slide we have, this is the number, and this is sign, exponent, and mantissa. All right? Number, exponent, sign, exponent, mantissa, the same here. And so I dumped this with a little C program to actually dump all the bytes of the double. And then I reconstructed, so I computed what this means actually and represented it as a fraction. So this thing actually is this fraction. And this thing actually is this exact fraction. Same here. So you see these fractions have nothing to do with the original number. You know, this number is not this thing. So why is the operation not giving a true result? Because the underlying numbers are this, and if you subtract this from this, you don't get this. All right, so why do we have all this mess? Why all these ones and zeros? Why is not this shorter? Why is not closer to this very simple number we have here? The reason is that, a fraction, if you have a number with a finite number of decimals, that's a fraction. You can multiply by the base, and you get a fraction. So they are rational numbers, actually, right? So this is an interesting result that is important for this talk. So a fraction in lower terms has a finite representation in some base if the denominator divides some power of the base. This is a key observation, let's call it that way. And we are going to see why. So let's take this number. You can remove the dot, dividing by this thing, and then you can eventually reduce this to lower common terms. I don't remember the term in English, but okay, so you get this. So if you start here, you get a fraction, and maybe you can divide something. So this guy here, divides some power of the base. You see? And the other way around. If you are able to start here, get a power of the base, since this is an integer, you're going to get a number with a finite representation. And if the base is 2, which is the case in computers normally, since 2 is a prime number, the only way you can get something that divides a power of this thing, it's another power of 2. So we have a corollary, which is that a fraction in lowest terms has a finite representation in base 2, if and only if q is a power of 2. And the consequence of that is that there are only, there are only this sense that can be represented with doubles exactly, these 4. The other ones are imprecise. So we are really fucked. I mean, there's no way you are going to work with this precisely. Almost nothing can be represented exactly in terms of sense using doubles. So that's the reality, and we have to avoid floats from day one. So in the project, in the kickoff, the instructions we were 3 guys. We agreed that we should avoid floats at all. I mean, not even an intermediate division, nothing, no floats. So if we could do object remove const float, we could do it, So no floats allowed. The first thing we tried was to work with integers, which is something I've been doing, in several projects in the past. So representing sense in integers, it's a common solution. Ruby has arbitrary-precision integers. You can transparently get integers of any size. This is the factorial of 100. It works very easy. You know that fixed nums are immediate values, which means they are, normally you have, in Ruby, stuffs are normally like pointers to structures or stuff like that, to the, in the case of C, to the structures that represent the data type you are working with. But there are some optimizations in MRI, and fixed nums are, stored up to a certain size in what could be a pointer normally. That's done with a little trick. So instead of having the regular range of integers at your disposal, you have 1 bit less. In that range, it's stored in the target pointer. and otherwise you go and get an alternative representation. So the thing is that the integer is shift 1 bit, and in the remaining bit, if you get a pointer, normally the first bit should be a 0. So the thing that MRI does is to store there a flag, which is not 0. So there's code that says if there's a flag, if the first bit is 1, then this is going to be an integer. So there's this kind of logic, hard code in MRI. And you, from this representation, you go and get the integer back, shifting to the right. Shifting to the right, yes. Okay, so if you get an integer that it's too big, MRI just switches to another representation transparently for you. This is the successor function, you know, which is going to give you the next integer given a previous integer. And that's the way it works. If the next guy is fixable, which means is representable in this, you know, within this range, is going to do that. Otherwise, it's going to promote it to a big num. With a big num, it's basically just a collection of digits using a big base, you know? So you have an array of integers, and each integer represents a digit. You do not have digits up to, I don't know, thousands. We have 10 digits, right? But conceptually, it's a digit in a big base. So the representation is compact. And then there's this is a whole field. I mean, there's a stuff, which base you choose, how do you choose the representation this way in order to have arithmetic that it's efficient. So it's a whole topic. But the idea is that you have an array of digits where the digit is something conceptually, it's a big number, and the base, it's big. So libtom math, it's a library written in C, very readable, and with a very good manual that documents these things, documents algorithms, and I don't know, the rationals for a lot of stuff related to this. So if you're interested in this, go Google for this. Is used also in Ruby News, at least the last time I checked it. So that's a good library for knowing more about this. We have some pros here, which is the integers are fast for representing cents, and they are exact, like, yeah, there's no ambiguity with integers. And there's something that I like, that is that they force you to think about the roundings you are going to do in the system. Like the first multiplication I showed has two quantities with cents. If you multiply two quantities with cents, you have to get some rounding somewhere because the result has to be cents. So you are really working in sets that are cents. You know, the operations are between cents, and the result is a cent. So that multiplication is not your ordinary real multiplication. It's a multiplication prime. You know, it's from cents to cents. It's a different multiplication. It's not the real multiplication. It doesn't have the distributed property. It's a different operation, you know? So I think it's healthy that you are forced to think, hey, we are going to need a round here. Which is the round? Which is the business rule behind that round? Cons. So you do not have you know, the fractional parts, so you have to build it to display it. It's not a big deal, but you know. And then multiplication and division, you need to do it by hand somehow, you know. Okay, then so this company wanted to have a little calculator in the website that allowed you to say, if, you know, in JavaScript, if I want to bet this money, I'm going, you know, automatically the calculator gives you what you which would be your profit, you know? But they also wanted that you could edit the profit. I want to win this money. How much should I bet? You know, they wanted to do both things of the calculation. And they wanted to do it for the backer. The backer is the guy that bets for something, and the layer is the guy that bets against that guy. You know, there are two players here. All right. So the thing is that, again, this division and multiplication is not the ordinary ones. So, if the guy that bets enters into the system this bet, and that's done, that's, you know, because this is synchronous, some guy bets something. This is stored in the seed. And then there's another guy that comes and sees that there's this bet. But he edits this quantity. And the problem is that for this division, this input and this input give the same result. So this is a strange situation because you are covering the bet, but you can tell the system, I want to bet this or I want to bet this, you know? So if the guy enters this one and this guy wins, the system cannot pay this guy. There's a missing cent, you know? This was a problem. So the first solution for this problem was the sidekick, which is just remove the feature, you know? This cannot be, it doesn't work. So solution, don't allow the user to do that. So the first solution for this was allow one side of the problem to do the operation and the other side to do the dual. And the dual is the same operation. So we would, the numbers would match. But later we had another problem, which is that you can partially see a bet. So let's say this guy bets $5, but then there are three people betting against this guy. One guy bets this amount, another guy bets this amount, another guy bets this amount. So the bet is covered, everything is seen, but if you add up this, you are not able to pay this guy. And the system has to be zero-sum system. So I had, you know, working this project, I had always a threat in my mind, trying to ensure that the property, you know, was satisfied and, you know, and get all the alarms on if something was off, you know? So you couldn't pay this guy. And this and the previous one are not things about representation. The problem here is a business problem. So you have to sit down with the stakeholders and solve this from a business point of view. It's not a problem with representations. If you are in the server with a notebook and a pen, you know, serving requests, like doing computations by hand, you cannot solve this. This is fundamental problem, you know? And the problem is that you are losing here some numbers, you are losing here some numbers, and the result is that this doesn't add to this. So it's not really, I don't call this a rounding off error. I'm calling this a business problem. If your business has to support partial bets and you want a zero-sum system, it's not going to work. It's impossible. That's it, you know? So another possibility was not allowing partial bets. A different option was that the company, you know, would take care of these cents with a special account or something, and if there's a missing cent, they are going to put it. Sometimes the difference is up, sometimes the difference is down. I don't know, it's up to them. They didn't want to you know, get rid of this feature, and there was a day that I believe it was just impossible to write this. The first thing you think of is big decimal. You know, many of you have used big decimal for these kind of things. Big decimal, in big decimal, the subtraction we did before works, you know? That's the big deal with big decimal. The internal representation of big decimal, it's conceptually similar to the previous one we saw. There's an arbitrary precision integer for the mantissa. So the mantissa we had before had like 52 bits, and now we have an arbitrary precision integer, so as much as your RAM can afford, you know? And this item is key. The base for this thing, it's 10 to some power of 10. So this is key. The base is 10 to some power, because this guarantees you, according to the result we saw before, that you are going to be able to represent exactly numbers that you write in base 10, you know, like the ones we are dealing with. So that's the key feature of big decimal. You can represent exactly things in base 10. Well, the base here is some power of 10, but if you get a number in base 10, it's going to be representable in any power of 10, you know? All right. And then there's an exponent, and that's internal stuff. So that's the key thing about the big decimal. It's represented this way, so you can represent exactly names in base 10. But big decimal does not solve this thing, which is that we have 1 and 3, and if you multiply 3 by this fraction, and you have exact arithmetic, this should be 1, but it's false. So big decimal is not like a magic thing that solves any problem with fractional numbers. Why? Because this fraction, if you think in base 10, it's periodic, right? It's 1 dot or 0.3 periodic, you know? So the representation of this number in base 10, it's infinite. And obviously, big decimal is going to store an approximation of this, but it's not going to be the real thing, because since the representation uses this representation, it stores the mantissa explicitly, it should need an infinite mantissa. You don't have an infinite mantissa. So big decimal doesn't work well if your problem domain involves divisions. And our problem domain involves divisions. You remember the division before? So big decimal is not a solution for our problem. So what do we do? Rational numbers. This is a data type that it's there, it's built in, and I believe is underused. Rational numbers, we have been seeing rational numbers all the time. Computers only, at least, you know, unless you work symbolically, computers only can represent fractional numbers. You are not going to be able to represent pi, for instance, or e. It's impossible, like in this positional system, you know? But the rational data type, it's a data type that is built in, and rationals are represented with 2 integers, like the numerator divided by the denominator. So you have 2 integers. And this can represent any fraction, any, as long as, you know, you can fit this in RAM, you know. So our constraint now is not the representation. Our constraint is memory. It's a different constraint. They have some nice properties, and they had the exact properties that we needed for our problem. You have exact representation of any number, of any fractional number. They have exact arithmetic. That's what we need. So you can add, you can subtract, you can multiply, and you can divide fractions. And the result, if you remember, when you do these operations with fractions, you get another fraction. you can, if you add fractions, you get a fraction. If you multiply fractions, you get a fraction. If you divide fractions, interesting, you get a fraction. So we are going to cover the four, fundamental operations in arithmetic with exact results. No cent is going to be lost. Indeed, we are, as a business decision, we are going to forget about cents. Because you remember, the thing is not about representation. The thing is that if you work with cents and you want to support partial matching, the system cannot be built. So we have to forget about cents. We have to work with not more precision. It's not enough to work with more precision. We need infinite. We need infinite precision for solving this problem. And there's another nice property in my mind that is that fractions are predictable across technologies, because we needed these things to work in JavaScript in the browser, to be representable in Ruby, and then we also needed in the database to be able to store money, to be able to store ratios, and these kind of things. The cons are you cannot tell the user that he bet, I don't know, 2/3. You cannot tell that to the user. You have to somehow represent that in a way that it's understandable. They are slower than other types. And this is something you have to, you have to gauge. It's fast enough. I mean, the real operations that I need to do for this problem are going to be a bottleneck. And in our case, it didn't, because we didn't need to do like very hard calculations or anything like that. You get a request, you get a couple of numbers, multiply a store, that's it. So the slowness compared, slowness relative to other numeric types doesn't matter in our case. And then persistence. Persistence, how do you store a fraction in a database? You could store a numerator, both integers in different columns, but then you lose SQL. You cannot order, you cannot add easily those numbers. So by luck, there was a binding to the GNU multi-precision library as an extension for Postgres. This is the extension. And this extension gives you a rational data type and also gives you an arbitrary precision integer for Postgres. So you declare, the stake of a bet to be irrational. And you can do some, you have all SQL with this new data type. And this is the final thing. This is the calculator, well, it's a little bit more complicated than I explained, but it doesn't matter. And in order to show this thing to the user, since the user still thinks in cents, we just put a plus sign here, which means we are working with more precision than cents. You have this indicated here, but the user interface, the only thing that has gone up to the user interface is this little plus in some places. You will not be able to retire, to transfer this little amount to a real bank account, but it doesn't matter. And with this thing, everything is exact. We could undo the sidekick and provide divisions. We can support partial bets, and I sleep very well at night. And that's it. Thank you.
Do we have any questions? Really? There's one.
Is there still?
You can't transfer money out of the system.
Yeah.
Won't there remain some cents in the system, some small fractions that cannot be sent out of the system?
Yeah, so the business trick here is that people bet points. So you transfer real money to system points, and it's one-to-one, all right? So that's true. If you have millicents, for instance, you are not even going to know which is the small fraction beyond cents. We only are going to use to show you a plus sign, and you are not going to be able to transfer those millicents. And this is a limitation of the gateways and the way money works in the world, So the stakeholders accepted that, that little property of the system. Yeah.
Anyone else? There's one.
Have you used the math-n library for any of this in Ruby?
If I've used it, yes, a few times.
I came across a bug in it recently. I was curious if you had any problems with it.
Yeah, I try to avoid that library. It changes the division. So one of the things that this math-n library that comes with Ruby, maybe if we switch.
Go ahead.
All right. So if you require math-n, for instance, then 3/2 gives you a fraction instead of doing integer division, and that's a global change. So yeah, I don't really like having that loaded. All right.
Okay, thank you very much.
Thank you.
Xavier.